My name is Bill Zajac. I'm a sales engineer for Teridion, and Teridion makes the internet 20 times faster. It's a very bold claim, but ultimately what we're doing is we're just doing route shaping to get content from the end user's desktop to the origin server much, much faster. So to start off, just what do we mean by these, why the internet sucks? So the way that this company was actually founded upon is our CEO is a cord cutter. He ultimately wanted to completely move to streaming services. He didn't want to rely on actual cable TV to provide any of his content, but he still had problems. So he did some research and he tried to figure out, well, how much actual bandwidth do these streaming services require on a consistent basis to my actual desktop or to my TV or anything like that. So from an HBO Go perspective, it only requires a 3 megabit per second connection. For Amazon Prime, 3.5 megabit per second. And the leader of the pack, the hog of them all, Netflix, only takes 5 megabits per second. So the question that he posed is, if this is happening, why do I have problems on a 100 megabit connection? Every single person on that left-hand side of the screen is a very, very forward-thinking company. Netflix has an amazing tech block. Their applications are optimized to the fullest. So how can they have problems delivering the content to their end users on a what we perceive as consistent basis? So ultimately, when we take a look at how applications are designed in general, again, this is very, very basic, but there's a client, there's a server, there's a link in between. And I come from the APM world, and I know there's a lot of tools and a lot of visibility that you can get into the server, into your data center, into your internal network, and into your client's desktops as well. There's a lot of RUM tools that you can utilize. But this link that is connecting both of them is still a gray box to a lot of individuals. There's limited control, there's limited things that you can do as an organization to take ownership of that point-to-point communication. And what that line actually looks like if we kind of zoom out is it's a much more complicated intricacy of multiple different routers connecting this from point to point. And what makes this more complicated is you have multiple ISPs that are involved in this individual communication as well. And not only can an individual ISP have internetworking issues, but then these relationships between ISPs also become a little bit hairy as well. Now, there are some solutions out there, and Nate did mention it, that CDNs are available to users, and they can serve content. They're meant to push content closer to the end user, but there are some circumstances and some use cases where the CDN really doesn't work. So what we really want to do is not necessarily make the internet shorter, which is what CDNs are doing. We want to just make this route faster. We want to not just rely on statically defined routes that ISPs are picking. We want to be able to pick out what's the actual fastest route from point to point. So we're going to do a quick demo on just how much of an impact this can do just from a US-based geography. So what I have here is I actually have a speed test server set up. The speed test server is located in San Francisco, and I'm just going to be running a speed test from this Wi-Fi to that speed test server. So don't download anything right now. So what I would expect from a normal bandwidth connection from a Wi-Fi, I'd maybe get 50% of the overall bandwidth for the Wi-Fi connection to a local speed test server. Right now we're getting around a 25 meg download and a 15 meg upload. I'm going to run that same speed test, but as opposed to going to a speed test server located in SF, I'm going to go to one in DC, just across the United States. And hopefully this works, or else I'm fired. All right, perfect. So what we're seeing around here is with that same speed test server just going across the United States, we're pretty much about halving our download speed. Let's do the comparison. 10, so 25 to 10 and 14 to 5. So just going across the United States, just doing a lot of the type of communication that we have to do to get to Amazon's main data center in Virginia, you're already losing a third of your bandwidth. Okay. So what's really going on in these routers, and why are they making these decisions, and why are they poor decisions from a very, very high level? Well, your ultimate client IP, after it gets resolved from DNS, is going to want to try to communicate to a singular source IP as well. That singular source IP is going to then communicate over to the router, and you're going to have a router that says, I'm not connected directly to that network, but I'm going to forward you on to someone who is. That router is going to say, I know that I have multiple connections to someone who knows something about this IP, but I'm going to send you to the most reliable one. And when we say reliable when it comes to routers, we don't mean the fastest. We mean the oldest one that's still performing, the one that has the lowest AS number. So it has nothing to do with speed. It has who's been awake the longest and who's still replying to me. So if that connection's saturated, if that connection has issues, but he's still responding, we're going to keep feeding him traffic. And then the next hop says, please hold because it's still congested. And then he forwards it on to the guy that says, I am actually connected to this network, and here's the origin. Now, this is a very, very small example of what actually happens in a normal circumstance with routers, or just with general internet connectivity. We ran some tests, and just to go from San Francisco to LA, it takes on average 30 hops. That's 30 individual decisions that these routers are making, and any single one can have one of these problems introduced. Any single one can immediately take your 100 megabit per second connection down to a fraction. And if there was some smarter way to route traffic, we might have been able to see that there was an alternative connection to ultimately get us to where we need as well. So the next type of component that we want to talk about is these internet exchanges. Internet exchanges are just giant data centers where ISPs come together and decide how they're going to share traffic, how they're going to transmit their data over to another person for either transcontinental or just inter-to-inter-network type communication. And how these ISPs make these decisions is basically two types of relationships. There's peering and there's transits. When ISPs of certain sizes decide that they want to start sharing traffic across each other, they normally establish a peering relationship, which is mutually beneficial. There's normally no cost associated with a peering relationship for either ISP. Whereas in a transit relationship, it's normally a larger ISP broadcasting himself out to other smaller ISPs, saying, I'm connected to a much larger global footprint, and if you want to get to this larger global footprint, you're going to pay me money for this. So it's more of a political relationship-based mapping as opposed to any really performance-based mapping as well. So a couple of examples is, let's say you have 3 local ISPs that are hosted on the West Coast. And because they're mutually of size, that A decides to have a peering relationship with B, and B decides to have a peering relationship with C. This is the fluffy side of the internet, where now because these 2 peering relationships have been established, not only can A and B communicate together and B and C communicate together, A can talk to C and C can talk to A through B. So this is really the free and welcoming internet. Now let's say that, again, we have 2 smaller ISPs that need to start talking to Tokyo. Then as opposed to them being able to peer with someone in Tokyo, they have to use some sort of true cable provider or true Pacific Ocean cable provider. And so now they establish a transit relationship with someone who can take their traffic over the ocean. Now the reason why I'm saying this is because this is where things get a little bit hairy when we talk about these different types of relationships. Let's say we have a scenario where A wants to peer with C. They have a lot of content that's trying to get to a network that C directly hosts. So A says, want to peer? And C says, no, I'm good. And this is literally 2 network engineers pretty much calling each other up and asking this question. Because C doesn't want to do it because he's already getting his traffic for free for a peer relationship of B. Well, A's an asshole, and so what he does, as opposed to just living with this, he routes all his traffic through a different way, which starts costing C money. So at the end of the day, because he wanted to ultimately peer with another ISP, he changed the routing table dynamically, not really looking at it from a performance perspective, just basically trying to get his way. So then what happens after C gets his bill and the CFO starts yelling at him, why are we paying for this transit relationship? He says, want to peer? He says yes, and then they establish the peering relationship. So these are just some of the problems that the internet basically comes up with, and it's not really, again, around performance. It's just around some of the politics that happen within these organizations. So what we're trying to do is we're trying to figure out a way of taking politics out of it, taking this failure that can happen. We really need, what we're talking about is route shaping, is at a snapshot being able to determine what's going on from a very, very high level inside the internet and forcing traffic to go along that route. And ultimately what we need in order to do that is we need to be able to see a heat map of the internet. We need to be able to understand where the problems are and not just notify customers saying, hey, your users are calling in from Chicago because of bad performance on Comcast. You need to be able to route around that. You need to be able to understand the quickest path from where the client is actually making the request from to where the origin server is located. And then what's really concerning is you need to be able to own the route, because there is really no one that can really connect every single house to every single server. There has to be a way that you can basically get that traffic going from where it's coming from to where it needs to go by having some sort of control of it throughout. And when the internet changes, when these dynamic decisions are happening all along the day, you need to be able to have your route changed along with that as well. So what does that look like? So first off, we need to build that heat map. So what we've done in order to get a global footprint is we started leveraging cloud providers. And what we did with those cloud providers is we had these measurement agents that are basically just taking network statistics of latency and throughput for not only inside of these different cloud providers, but their neighbors. So we're just basically doing a lot of trace routes. We're doing a lot of latency tests to be able to build what's going on around me, and then we're reporting it into, down a slide, reporting it into a big data analytics database. This is where we're able to just get a pure graph of what's really going on from a point-to-point perspective, as well as just the internet health in general. Now, because if we want to be able to get our own routers or be able to manage traffic, we need to deploy some sort of physical software or hardware around the world as well. So one of the things that we were able to do is create basically a router within a Linux VM. So we're able to deploy these inside these same cloud providers, and this is where we're able to take ownership of the actual traffic route. So when a user actually queries for that server, they basically, as opposed to getting pointed directly to the origin, which is what the domain name service would normally do, they'd point to our cloud router IP. So we can take ownership of it. And since we basically set up a relay race, we can then point it over to wherever we need to go. Maybe it's another cloud router. Maybe there's a faster path, so we have it shaped to a different cloud router. And then ultimately, let's say that there's a new cloud provider that comes on board that has a much faster router and much faster optimization for us. Because we own these different cloud routers at different areas, we can then dynamically shape it to that area as well. Now, the real question is, does this work? So what I'm going to do is, again, very similar to before, is run a speed test. But we're going to put it to the max. So this is a speed test server now, again, running from my client VM. We're going to do a speed test over to India. Okay? So this is regular internet. Regular internet from this Wi-Fi to India. So we're getting a little bit smaller numbers than we had before, which is expected. We got to go across the Pacific Ocean. We got to go into Bangalore. So right now we have about a 4.8 meg download and a 0.71 upload. So let's see what happens with Teridion. Wow. Okay. So let's compare it to this one, where we had a 4.8 download, 0.71 upload. We had a 44 download, 94 upload, 12 upload. Let's go to the regular speed test that's located in San Francisco, just down the street. 25 download, 14 upload. So just by, again, all we're doing is we're just route shaping the traffic from point to point better. We're just finding the quickest path from the actual client request to that origin data center server. We don't own any infrastructure. It's just utilizing the least congested path in between those 2 points. Now, how do you apply this to something like an actual customer use case? Obviously, we can't just go around and show people speed tests and say, look at what we're doing. So we have to show them something that can actually be something beneficial to an end user perspective. So what I have here is I just popped over to a Linux VM that's hosted in EC2 West, so here in San Francisco again. And on the left-hand side, I'm going to be doing an upload over the Teridion network. And on the right-hand side, I'm just going to be doing an upload over the regular internet. We're going to be going to an S3 location in Ireland, an S3 location in Japan, and an S3 location in US East. We have the same 100 megabyte zipped archive file going to each one of these locations. And I'm going to race these guys. So if I was an end user, and I just sit there and put in my actual Excel spreadsheet and try to hit submit or some case that I had to wait for this guy to complete, I'd much rather have the left-hand side. So all we're doing in this is basically we're utilizing Amazon's S3 API to do an upload. What we've done in the back end is we basically changed the domain that you're uploading to. As opposed to the standard Amazon domain, we've created an accelerated domain that we're leveraging for this. So there's no code changes on your side. So this is basically a layer 2 and layer 3 technology. Ultimately, what you're doing from an implementation perspective is you're taking your domain. We give you an accelerated domain to CNAME over to us, which we use on S1 for this, and it wouldn't work for us if we didn't use on S1 because of geolocation for our client IPs, and it's an amazing feature. Pitch. But it's so no hardware, no software. So that's a good point. So mainly, it's really easy to show throughput acceleration with the technology right now. We are working on what we're calling latency acceleration or latency consistency with this. Preliminarily, we are seeing really good results because ultimately what we're noticing is we're not only getting better times the regular internet performance, we're getting a consistent value as well. So if you have a 20 megabit per second connection at home with a Teridion powered app, you're always going to get 20 megabits per second to that end user as well. So from a gaming perspective, we're going to reduce latency, reduce ping. The question is, can we only do this because we're in the public clouds? The answer is sort of yes. The way we're able to have such a large infrastructure is we are leveraging multiple public clouds. So right now we have API access to over 15 different public clouds, and we're able to spin up these routers in basically over 150 different geolocations on demand. So we couldn't do this 15 years ago, correct?